Question 13, and this is the canopy problem which derives from question 12. In this we're looking at a torsion problem in that section, and the architect has allowed for an edge member, an edge beam, which is a channel section with its toes down, as we say, so it's on its side, so it's quite thin on elevation, and it's now supported by a backspan. We're taking away the fixed supports, the walls in the building, so essentially it's a cantilever with backspan action. The backspan is 200 by 90 PFC, and we've got a tapered section channel, and that's welded to that, so it forms a backspan. And the figures: 2.9.8, 2.9.9, 2.3.2. In chapter 2.9, 106 et al. Will go through the methods used in this, so it's quite extensive. Question 13a, and now we're going to set this up. We've got the cantilever, we've got the PFC on the edge, cantilever edges, so this is looking at the end. Toes down, the I value is given, 315 centimeters to the 4, and the beam diagram is 1 kilonewton central point load on a 4 meter span, reference figure 2.2.3. The deflection under load at the mid span is PL cubed divided by 40 ATI. Putting in the figures with consistent units, again I use newtons and millimeters. This gives us a deflection of 2 millimeters in the center of the edge beam. Question 13b. Draw this out, and there's the backspans, and the backspans are, if the cantilever is L, backspan is 2L. It's got 150 millimeter deep average section. We've got the PFC toes down, ref 13a, and we take the average values for the cantilever section, assuming 150. pH cubed over 12, which is the I value, gives you 337 centimeters to the 4. And we look at the deflection of this with a 0.5 kilonewtons, which is the reaction force. You can see from the diagram. PL cubed over 3 EI from figure 2.3.2, as if it was a pure cantilever, gives us, putting in the numbers, 0.81 millimeters. Now if you go to figure 2.3.5, you can pro-rata this for the cantilever with 2L backspan and the pure cantilever, so it's 8.5 over 3 times that deflection of 0.8, which gives you 2.3 millimeters anticipated deflection. Question 13c. And what we're going to do now, just draw this out, we're going to total up the deflections. So just to draw this out so it's clear, we've got 2 millimeters in the middle of the toes down channel, 2.3 on the ends. So the aggregate figure is the total which we add together. The total deflection, if you like, of the cantilever system is 4.3 millimeters, 2 plus 2.3. And this is based on superposition, which is a useful principle. And now we're going to look at the comparison of stiffnesses. Question 13d. This is where we're going to look at the relative stiffness of the two systems. So if you recall in question 12c, that we had a PFC fascia beam and we found the deflection was 158 millimeters, and then we altered the design to the PFC edge beam with a backspan, and that had a deflection of 4.3 millimeters. This could have varied depending on the method of solving, but if you wait until the end of this video, you should see what I am talking about. So the relative stiffness of A to B is 1 over the deflection of A divided by the deflection of B, where A is the backspan system, which is 4.3 millimeters. B is the previous system with the PFC fascia, and the relative stiffness of the backspan to the PFC fascia is 1 over 4.3 divided by 158, and that gives you 37. In other words, the backspan system is 37 times stiffer than the fascia PFC original from 12A. This ends the main video. But some of you might be wondering, on 13B, when I adopted the section which was the plated section, which was equivalent to the cantilever for the backspan, what would have happened? Many of you would have attempted to use the PFC, and by using a slightly different method, this is to demonstrate that the deflection would have been somewhat less for those of you that did it that way. So the beam was a 3 meter backspan, 1.5 meters cantilever, 0.5 kilonewton load, and a backspanning beam 200 by 90 PFC. And the assumption in this is that we're going to ignore the flexural deflection of the cantilever section, the tapered section, which is welded to the PFC. So we just take a standard beam, a standard simply supported beam, and the rotation is given by ml over 3 EI, where m is applied to the end of that beam, and the moment is 0.75 kilonewton meters, the backspan length is 3 meters, E is 205, E3, and I was given before 2523 centimeters to the 4. Putting the figures in with consistent units, we come up with 1.4 times 10 to the minus 4 radians, and the deflection at the tip of the cantilever is given by that rotation times the cantilever length, which comes to 0.2 millimeters. So recalling where I used a lesser value, which was the cantilever section for the backspan, as an assumption, in which I got 2.3 millimeters, your total deflection for the simply supported toes down channel and the backspan effect on the tip deflection would have been 2 plus 0.2, which would have been 2.2 millimeters. But in the grand scheme of things, neither 2 nor 4 are going to trouble us in any way. Thank you for listening.